Good day. My name is John Walkinshaw. The topic is retaining walls and how they have been used by public agencies and the private sector for holding soil in place. The objective is to expose you to the many different techniques that have been tried and are relatively easy to build. But first, a little bit on my background and some formalities that must be made. My present position is Regional Geotechnical Engineer for the Federal Highway Administration out of our regional office in San Francisco, California at 211 Main Street, Suite 1100. The zip code is 94105 for any of you listening that may want to contact me on the subject matter that is going to be presented. In case you're wondering about my accent, it is not from down under, as my introductory good day might have misled you to believe. I was born in the United States of British parents. At a very young age, they moved me to Switzerland. 18 years later, I received the equivalent of a bachelor's degree from the École Technique Supérieure de Genève in Switzerland. I then came to the United States and obtained a Master of Science degree from the Massachusetts Institute of Technology. I have been with the Federal Highway Administration since 1969 and in my present position in San Francisco since 1975. I'm a registered professional civil engineer in the state of California and also a registered geotechnical engineer in the same state. A few credits. I'm an avid photographer, and a good number of the slides you will see are those that I have taken myself. The others represent a collection that I have accumulated over the last 15 years through exchanges with engineers or manufacturers throughout my travels. It is not possible to name them all, but their contribution is greatly appreciated. The engineers from one public agency have been particularly innovative in this area. They are from the Forest Service and the U.S. Department of Agriculture. Their retaining wall design guide covers a number of the systems discussed in this presentation. A copy can be obtained through NTIS in Springfield, Virginia at zip code 22161. The accession code number is PB816760 and costs about $29. When appropriate, I'll give the names of specific products shown. Because of this, I must preface my presentation with the following disclaimer. The contents of this presentation reflect the views of this speaker, John Walkinshaw, and I am responsible for the facts and accuracy of the data presented herein. The contents do not necessarily reflect the official views of the Federal Highway Administration. Trade or manufacturers' names which appear herein are cited only because they are considered to suit the objectives of this presentation. The U.S. government, including the DOT and the Federal Highway Administration, does not endorse, advertise, or promote products or manufacturers. I'll be working mostly with photographic slides of actual field applications. I have divided my presentation into 6 parts, which can be used individually or in combination. These are, the first 2 generally fall into the category of mechanically stabilized embankments. The first one is what I call geotextile walls, and the second is geogrid reinforced embankments or geogrid walls. The third is what I call prefabricated or lightweight facings. The fourth, gravity or cantilevered walls. The fifth, salvaged materials and other common highway products. The sixth is a short one discussing erosion control and soil bioengineering. Where appropriate, I'll point out problem areas. I wish to emphasize that they are not product failures, but human failures. Typically, they are problem areas that come about because of improper construction or failure to recognize the problems of water, which have been discussed in other portions of this course. Now that the formalities are over, let's get on with the show, and let's have the first slide. The topic is retaining walls, and of course one of the items that we must consider is if you want to be able to solve some problems, you've got to know what types of retaining walls are available. And this is why in this presentation I have put a lot of slides together. Probably much more than would normally used in any one presentation, but they are there so that for those of you that are going to be giving this presentation in the future, you can select those that you feel are most appropriate for the audience that you will have. There will therefore be some duplication or some apparent duplication in the whole set that you're going to see. As we go throughout the presentation, we will see that there are different types of retaining walls that fit the site better than others. And hopefully at the end of this presentation, you will be able to see which ones are more appropriate for the site conditions that you have. In the introduction of these slides here, the first 10 or so are going to be showing basically what I call mechanically stabilized embankment walls, or MSEW systems. The first ones are just to give you a brief history of what has happened in the last 15 years on particular ground reinforcement systems. And presently what is available commercially in the United States. These particular slides or systems that I will be showing are not those that could be built by maintenance forces, but are just here to illustrate what is available and to what extent the technology has gone today. We will talk briefly about reinforced earth, BSL's retained earth. We'll also see later on in the presentation Hilfiger's welded wire walls, and a number of the other systems such as the RSE, which is reinforced soil embankment by Hilfiger. Then, of course, as I mentioned earlier, specifically the types of products that people in maintenance or highway departments could build themselves are going to be the geotextile or fabric walls and or the geogrid walls. In these systems, in the mechanically stabilized embankment systems, basically we're dealing with three types of elements. We're dealing with a facing element, which is illustrated on the left of your slide. And that facing element, as we will go throughout the presentation, you will see, can consist of any number of things, anyway from concrete to as lightweight as a geotextile or engineering fabric. Then, in these mechanically stabilized embankment systems, there is some kind of tensile member that is laid in the ground to reinforce the soil. And this tensile member can be anything from, in the terms of the original products, steel elements, or as we will see, they can be geotextiles or engineering or geogrids. So basically what we have is these three elements, the facing, the reinforcing, and of course the backfill material that you place around the reinforcing itself. So these are common to these mechanically stabilized embankment systems. In terms of applications, basically what we have here are illustrations of different combinations that you may want to consider. There are the systems where you actually support the roadway directly on top of the mechanically stabilized embankment system. You can have as shown in the middle of the slide, a structure supporting an embankment. Let's say that you were on very steep slopes and you were having problems with the catchment area, and you can place a mechanically stabilized embankment to support the system. You note that there is a difference in the cross-sectional area of a system where there is no surcharge, just as shown on the top slide, top of this slide, where there's no surcharge, the roadway is directly on top. Or if you've got a surcharge such as a sloping fill, the volume that has to be reinforced is quite different. And you should get some technical advice as to, if you get into large projects, as to how these have to be designed. The retaining wall manual that I mentioned earlier does cover some of these items. The lower portion of the slide shows a system where, in fact, the reinforced volume is placed on top of an embankment. This is similar to the second case, where we're trying to reduce the amount of fill that has to be placed, and because you're in steep terrain and you can't get a catchment area. The first system that was originally developed, and which is sort of the basis for all this, is a system called what we call in this country reinforced earth, and which has got some patents attached. And actually it's a system that was developed by a French engineer, Mr. Henri Vidal, back in the mid-1960s, called Terre Armée. The first project that was built in the United States is illustrated here, and what we see is a metal skin facing off to the left, and the reinforcing in this element is reinforcing strips, or metallic strips. In this system, it has been modified a number of times, and presently what we see are concrete panels which are prefabricated, which fit into each other and tied back with strips, and a granular backfill is typically used for this system. The point to be made here is that very high walls have been built with these systems. We're talking about walls 30, 40, 50 feet, 60 feet have been built with these reinforced earth systems, or some of the other systems that I'm going to be showing in the next slide. This particular slide here illustrates a modification of this reinforced earth system that was originally made by Caltrans, but then picked up by a number of different companies. And this is VSL's retained earth system, which uses, instead of strips, uses a reinforcing mesh to reinforce the soil. You'll note when we get into the geogrid systems that basically we are also using the same concept, a mesh to reinforce the soil. But initially this was a steel mesh and is used for the commercial product by VSL, which is retained earth. Just to illustrate that some very high walls have also been built with the system. This is some slides, or a slide of a wall that is just being finished right now, the summer of 1988, in Northern California near Cloverdale. This is a wall, when it's completed, will be 62 feet high with a batter of 1 in 48. The very high walls have been built with these commercial systems, and they are beyond the scope of what maintenance would do, but basically you'll see that the concepts that were used with the geotextiles or the geogrids basically follow these commercial systems. This is Hilfiger's concrete-faced system, which is reinforced soil embankment, and its panel is somewhat different. It's a little bit more elongated, and this is what this system looks like. Let's get down to some of the systems that have been built by local agencies, and fabric walls or geotextile walls. Basically, all of these start with one or two types of geotextiles. Illustrated here is a non-woven type of geotextile, which is usually the most commonly used and somewhat less expensive than the woven type fabrics. And if you look at a close-up of one of these fabrics, this is what you'll see. Basically, the mesh intertwine. They are sometimes bonded, sometimes not, sometimes they're mechanically interlocked. It really doesn't matter. The fact is that the fibers are just random, and they are basically what we call non-woven. Illustrated here is a woven fabric. Here it's just like the type of fabric that we wear every day. The strands have been laced together, and typically these fabrics come in are much stronger than the non-woven. Fabrics or geotextiles have been used to reinforce pavements, and they basically are delivered to the project site in rolls. Typically, if you see a lightweight or a light-colored fabric, it means that it hasn't been stabilized for UV protection, although there are obviously some exceptions to that. But one of the problems, the earlier problems with using some of the geotextiles was the fact that people didn't recognize that if these fabrics are left exposed to the sun, that they deteriorate. And that is why, since then, some of the fabrics have or include some kind of coloring agent to increase the resistance to deterioration. How does a fabric wall go together? Well, basically, instead of using the metal strips, we're now going to be using the geotextile to reinforce the soil. So it's basically the construction of an embankment which alternates layers of fill with layers of fabric. The fabric is wrapped around the front face to hold the soil on the front face of the wall and lapped back. As you see on the top layer here, there is a lap that comes back, and that typically is in the order of 3 to 4 feet for most of these fabric walls. Any type of fabric obviously can be used. This is a commercial slide, and I'm not advertising the specific product. The Forest Service was one of the first agencies to try out the use of these fabrics or geotextiles for building walls. And here we see one of the earlier walls built in the Pacific Northwest, and using available backfill material. And here in this case it's a nice granular backfill. And then the fabric is, as you can see in the lower left-hand side of your screen there, is a white fabric, one of the earlier fabrics which was not UV protected, and therefore something had to be done to protect the front face. On these earlier projects, all that was done was to spray the front face of these fabric walls with hot asphalt, as illustrated right here. And of course, this is what the fabric wall looks like. Is probably not the most pleasing in terms of aesthetics, but is certainly functional for the type of road systems that the Forest Service deals with. You'll note that there are some pipes sticking out through the front face of the wall. These pipes are included so that the backfill doesn't get saturated. And with most retaining wall systems, it is important to get drainage, handle it either behind the wall, through the wall, or in some fashion so that the backfill does not get saturated. Of course, once the geotextile, which was originally permeable, was sprayed with asphalt, then of course it's an impermeable membrane, and this is why these pipes have been included in the front face. Another way of protecting the front face is using shotcrete, and this is illustrated here. And again, this is purely for protection of the fabric, and of course, if you anticipate any vandalism, you want to put some kind of facing on it that is more durable than, let's say, the asphalt. As I mentioned earlier, the earlier fabrics were not protected, UV protected. Some of the more modern fabrics are, and typically these fabrics are dark in color or black because they've got this carbon black that's been introduced in the manufacturing process to protect them from the sun. Fabric walls have been used by highway agencies for temporary structures, and this is one that I'll be talking a little bit more about in terms of construction a little later on. and for widening of a project or doing some major maintenance on the project itself. And this was built as a temporary structure so that traffic could be moved over, and the construction work could be actually done on the roadway itself. The wall was built because off to the right, which cannot be seen, there was a marsh area which had to be protected from an environmental control point of view. These fabrics are typically delivered to the project site or obtained, and they are in rolls, and they are typically wrapped, and they should be maintained that way so that there is minimum exposure to the sun. Even with these protected ones, you want to make sure that the fabrics are protected. First process in building one of these fabric walls, of course, is to cut the fabric to the proper length. And then you have to lay it out, and you need to form the front face. And the next few slides here are going to illustrate how this is typically done. In this particular project, a number of different fabrics were tested, and this is what you see here. There are two different fabrics, one off to the left and off to the right are different fabrics that were being evaluated in terms of strength for this particular experimental project. What I want to point out in the back is this temporary form that is being used. There's an angle iron that is welded onto a little strip that comes into the backfill, against which a board will be placed so that the front face can be formed. Then we see some fill being placed on top of the fabric, and then the workers here raising the form, putting it vertical, and here's a close-up of that process where the form is erected, the fabric is being readied to lay down up against the form, and then the excess, which is going to be rolled back, is going to be flopped over the front face of the wall. And then the process is repeated over and over again to come up with the total wall, as illustrated here. Again, you see some pipes for drainage. This wall was also part of an experimentation, so there was also some instrumentation included. This particular project was in Colorado. Then the next phase, of course, is backfilling the fabric against the temporary form, as we see illustrated here. The fabric is flopped over the front face, the excess, which is going to be brought back over. And then here we see typically walls are not built vertically. They do have a regular batter on the system, and that is you find it's a whole lot easier to build if one has a batter such as illustrated here. On this particular project, there was a number of tests performed to find out how well different types of fabric were used, what strengths were needed. The U.S. Forest Service Guide discusses the design of this, and again, I recommend that this is a reference that one should obtain if you're interested in building these types of retaining structures. What we see on this slide is a worker putting in some instrumentation. This would obviously not be a common thing that you would see on a regular type of fabric wall. I mentioned that it was an experimental project, and of course, with most experimental projects, you want to have some very close control for the construction. And here we had a junior engineer that was very dedicated and wanted to get this experimental project going very well. And so he was sent out to the project to make sure that it was built properly. Of course, very young and very eager to get the job done properly, and an experimental project not the favorite for contractors. And this fellow was, well, a little bit more ambitious and got in the way and started telling people what to do. And so the contractor decided to dedicate the wall to him. And here he stands in front of this wall. Of course, this is this is just a joke. The point that I want to make here is the fact that architecturally, with the finish, you can do anything that you wish for these walls. Here is just being shotcreted. It was a temporary wall because it was being used by the contractor, and it really doesn't matter that you know what the facing looked like. It can be finished off in more detail if the agency wishes it. Are these systems strong? Yes, they're very strong. And this particular site, again in Colorado, originally some of these walls were built with the intent that they would fail when reaching the final height. Again, they were experimental projects. And after the project was built, none of them failed. The contractor used the walls for the access road throughout the project life. And then they decided to see if they could fail them by putting a surcharge on them. And as you see on the top of this slide, they put another 15 feet of surcharge on top of these fabric walls and still were not able to get failure to occur. Just another project, same type of sequence. This is that temporary wall in Oregon. Here you see them using the temporary forms again. In this case, they used 2x4s laid in the fill to provide the horizontal member here, and then braced it with wood, as you see here. This was a temporary structure also, and here's the same construction sequence. You'll notice that they are trying to make it a little steeper, and of course, if you don't get compaction close to the front face, then you have some problems of maintaining the alignment of these temporary forms. And of course, then the individual layers are not very uniform. Again, it was a temporary wall. Aesthetically, it didn't matter, but that is something that one should consider when building these as permanent structures. You also note that the contractor was having some problems getting lateral support for his temporary form, and had to go all the way down to the bottom of the wall to support some of these. And so, again, because there was a little bit of problems with the compaction of the front face, there was some sloughing, you end up with having to do a little bit more work on terms of the bracing of the wall. And this is just another illustration of this. Again, the wall gets higher, having difficulty getting alignment, and the bracing gets longer and longer. This is basically almost at final elevation. Now, if you want to get better quality control on the front face, use a material that's easily compacted with minimum compactive effort, and then in this case, this would be a granular type soil. This is a project in New York, and this is a permanent structure, and the state was going to shotcrete the final face, and obviously shotcrete is fairly expensive, so you wanted to have fairly good alignment on the fabric itself. And off to the left of the screen there, you'll see the string line off of which the contractor was working, the temporary L-shaped braces that were used by the workers to support the board for the temporary facing, and a very clean granular backfill to get good compaction. Obviously, you could just to get good alignment at the front face here, what you could do is just use a little bit of aggregate type material right at the front face to get the good compaction, and then the rest of the fill could be your whatever you have on the site. Of course, from an engineering point of view, you have to design the wall itself, the length of embedment, based on the properties of the soil that you have. This is what the wall looks like nearing completion before that the shotcrete is placed. This was one of their first walls. It was also instrumented. In terms of drainage, as you saw, they had a very good clean granular backfill, and therefore the drainage occurred behind the fill itself, behind the face itself. Just another shot of this, and you can see some nice clean alignment on these walls. And of course, here's the finished product with the shotcrete on the front face. So in fact, this engineering fabric wall with the shotcrete facing from a public's point of view just looks like a regular concrete wall. Let's turn to a different type of backfilling operation. Here we see a site again up in one of the forests built by the Forest Service, and here they are measuring the length of the that they're going to have to use for the fabric itself. That's the first operation, and then laying out the fabric against the temporary form. You will see that the backfill looks somewhat different. This is actually sawdust or wood chips that are used for backfill. This is obviously an available material up in the mountainous areas, and of course it's a very lightweight material. And when you're dealing with slides, this is what you want, to reduce the driving forces. If you have lightweight fill material available, this is one of the options. And so this is a engineering fabric wall backfilled with wood chips or sawdust. Here we see the material being brought, and here you see the whole phases of the material on the front face, the fabric that's already been laid across the forms, and the truck bringing in some more of the wood chips, wrapping it around, and then spreading it out. Typically, obviously, this material is difficult to compact. All you do is run over it with a few times with the available equipment, and that seems to be sufficient to get adequate compaction. And this is a 26-foot high sawdust backfilled geotextile reinforced wall. So again, different type, same type of concept, but different type of backfill material used to reduce the driving forces in the side. Other types of fabrics that have been used are for reinforcement are just materials that are commercially available, like chain link fence. Here is some chain link fence that is being tested in a large direct shear box at the transportation laboratory in Sacramento for Caltrans. And this has extremely high pull-out resistance and has also been used for low types of retaining walls, as illustrated here. Again, another Forest Service application. Now, of course, here the material itself is somewhat more expensive than the fabric that the geotextile that one buys, and so you want to use less of it. It is also stronger than some of the lightweight fabric, and therefore you want to use higher or thicker lifts between the reinforcement that we see on the project. And so, of course, you're going to have some bracing on the front face that is a little bit more stout, so that you can, in fact, use and have these larger lifts. Again, a batter is useful because it's very difficult to build vertical walls on here. So this is during construction, and here we see a detail of these fence walls, if you will, fabric walls. Another application. Low walls, but quite effective. And here's another one. Just to show you that there have been other applications of geotextile walls, here is an application in France used for a spillway, which was built with a special type of geotextile. Now, this was a UV protected, ultraviolet protected system. Very expensive fabric, so therefore you also want to use less of it, and therefore the same principles as with the fencing material. You want to use less of it, so you want to have higher lifts. When you go to higher lifts, you run into the problems of how do you hold the front face. And if you want to get an almost vertical front face, you'll see that the bracing system then becomes much more significant, and it could, of course, increase or does increase the cost of the construction of the wall itself. So there's basically some compensating factor. You buy a more expensive fabric so that you can increase the thickness of the lifts, and have less layers in the system, but you're introducing, as you do that, more construction problems in terms of maintaining the face in alignment and so on. Here's the completed view of this little spillway, and here it is in actual operation. So this concludes the first portion of this on engineering fabric walls, and I'll entertain any questions that you may have at this time. The first session we talked about the use of geotextile or fabrics in the construction of retaining walls. We'll now move on to products that are typically stronger than engineering fabrics, which are called geogrids. May I have the first slide, please? As illustrated on the top of the slide, geogrids come in a number of different forms. Typically what we're talking about are nets or grids that are made of plastic. On the bottom of the slide are what we talked about earlier, which are the different types of geotextiles. Geogrids come in a number of different formats, and a number of different companies produce these, and just a couple of them are illustrated here. One of the first products to come on the market was the Tensar line, which originally came from England and over to Canada, and then is now manufactured in the United States. A number of other companies, Signode, Mirify, also produce these types of products. They also come in a number of different shapes and different strengths. And like I mentioned earlier, the strengths are typically quite a bit more than what you see in the geotextiles. Some of these products have tensile strengths of several thousand pounds per linear foot, which is obviously quite strong. They also typically come in rolls. Here's one of the tensile products, and are delivered to the site in rolls that come in different widths. In the tensile product, typically we'll see the widths that are in the order of 3.3 feet, which is 1 meter. And they typically have to be clipped together if you want to use larger widths, such as illustrated. The little clips are shown in the middle of this the screen right here. One of the first applications of ground reinforcements in the North American continent was done up in Canada for reinforcing a failed embankment under a railroad. As illustrated here, the lower portion of the rebuilt embankment had a slope of 1.5 to 1. That's horizontal to vertical. And the upper portion of the embankment, which is on a 1 to 1. Obviously this slope is steeper than what the natural materials can support, and this is what we use these geogrids for, is to be able to build steeper than natural angle of repose slopes. Here's a few slides of that original project. Again, these slides are not those that I took myself, but are some that I borrowed. We can see that the rolls are about 1 meter in width, and were laid down on between the layers of embankment, and then are going to be wrapped around the front face. This is an illustration of one of these this embankment under construction. One of the things that one has to be conscious of is when one raises the slope of or the angle of repose or the angle of slope on these embankments, then there's a potential safety problem of workers on the edge of these slopes. Someone that trips and falls on a 1-to-1 slope will have great difficulty in stopping before reaching the bottom of the slope. So that might be one consideration as to the height that one wants to build any one slope that's oversteepened with these geogrids. Illustrated here, you can see that there's a fellow standing on the slope, and he is standing on a ladder that is in turn being supported. If you now look at the lower right-hand corner of your screen there, you will see that there is a fellow holding up the ladder that the gentleman in the middle of the slope is standing on. So one has to consider the safety aspect of construction when building these very steep or over-steepened slopes. In this case, you can see that the geogrid has been used and wrapped around the front face to hold the front face material in. And this is a view of the completed embankment. On lower angle embankments, and typically slide problems that have occurred down in the southeast, where they have very large quantities of clay, or basically that's the only type of material that they have to build embankment with. Sometimes failures occur on slopes that have slope angles as low as 3 to 1. This is a case of an embankment down in Texas that was excavated. The failure material was excavated, and then the same material was replaced, reinforced with a geogrid, as illustrated down in the lower right-hand corner of your screen. This is the actual construction process. This was one of the more lightweight type of products that Tensar produces, and it does come in roll widths that are wider, which are obviously easier to work with also. And here we just see the workers laying out the fabric and then backfilling over the geogrids to build the embankment. There is nothing that is done at the front face to prevent erosion, since on a 3 to 1 slope, typically vegetation can be generated without any additional reinforcement needed. Here's a close-up of this material, again showing one of the lightweight grids with the backfill material placed in it. This is another site where it's a little bit more granular. When designing a correction for a slip-out, a small landslide, an embankment that has failed, typically you can see at the lower left-hand corner how one can rebuild this failed embankment using geogrids. Typically, if one looks at the design charts that are produced by the various manufacturers, you'll see that there are more closely spaced geogrid layers down at the toe of the embankment, because that's where the stresses are the highest. And as one reaches the top of the embankment, these layers can be spaced out. These are all discussed in the various product manufacturers' brochures and are beyond the scope of this presentation right now. There are a number of ways of analyzing these. This slide is just included to show how one would typically go about this, analyzing the slope stability as been discussed in the course, plus the geogrids then are added to the slope to increase the resistance force and therefore increasing the factor of safety. Again, this is another slide showing the cross-section of an embankment reinforced with geogrids, and the geogrids are illustrated here to have different functions. Typically, you'll have them, again, more closely spaced down at the toe of the embankment where the stresses are highest. You may need some geogrids placed close to the face because it's over-steepened, and you're going to have to handle the problems of erosion or instability that could occur close to the face. So one could have shorter segments reinforcing the front face of the embankment, and then wider spacing for the overall reinforcement as the embankment gets higher. First little case history. This is again from the U.S. Forest Service, and this is a small embankment failure, and they used the wide strips of geogrid to reinforce this embankment. Again, they had fairly granular material, fairly high shear strength material, good material to work with, but it is fairly close to its angle of repose, so it's reinforced with a geogrid to improve its factor of safety. One thing that you'll note off to the left of the slide is the use of prefabricated drainage systems. These are systems that are available commercially. They consist of a plastic core which is surrounded or wrapped around with a geotextile, and it's the core itself that allows water to permeate down through this prefabricated drainage system down to a conventional drainage pipe exit at the bottom. The U.S. Forest Service have used this system quite extensively for their landslide corrections, and are very satisfied that these prefabricated systems work quite well. They've actually done quite a bit of experimentation of these different systems, evaluating them, and their office out of Pleasant Hill, California, which is in the San Francisco Bay Area, has run most of those tests. Of course, the embankment is then built conventionally, just adding these layers in between, and of course compaction is important. And then in this particular case, instead of wrapping around the individual lifts, they used a geogrid draped over the front face to help resist the erosion forces due to rain and allow some vegetation to occur and take root more rapidly, as illustrated in the follow-up slide that's shown right here. In this case, so the natural angle of repose is such that the front face does not need to be additionally reinforced, and the fabric here is just draped over the front face, and this works quite satisfactorily. However, when you get into steeper slopes, then something has to be done. This is a case history of a embankment that was built on the University of California campus in Berkeley, California. It is a 70-foot high embankment which was reinforced with a geogrid. The design angle between the benches that one sees on this cross-section is 3/4 to 1, horizontal to vertical. It's a very steep front face. You notice that the designer has drawn some very nice straight lines that go from the toe of the embankment up to each level of each bench and on up to the top of the slope. The average slope is about 1 to 1. And this embankment was built for two reasons. One, it was a way of using some waste material that was being taken out of an excavation further up the mountain, and it instead of having to haul all this material away and drive it through town, they decided to build this steep embankment to create some more parking space, which is direly needed in these hills that are around the campus at Berkeley. One of the problems is, as I mentioned earlier, how do you build a very steep front face? There's the safety problem and the physical problem. How does one get good compaction on the edge of a very steep slope like this, and especially when you're trying to wrap it around, which is essentially what we have here, about 4-foot lifts between where the geogrids go. In this slide, the first lift shown at the bottom towards the left of the screen is the only lift that was possible to build at the 3/4 to 1 slope. the contractor was having extreme difficulty in maintaining the alignment that the designer wanted and getting the steep angle in the material to stay in place while the geogrid was wrapped around the front face. An alternate was proposed in which the geogrid, instead of being placed on the 3/4 to 1 slope, would be placed on a vertical slope for 4 feet and then offset 3 feet, giving the same end slope of 3/4 to 1. So this embankment, instead of being built on a uniform slope, was actually built with these stair steps built into it, mainly because of construction problems and how one gets compaction near the front face of the material. There's one thing that one has to realize when dealing with these materials is the fact that they only work in one direction. They only work in tension. They do not work in compression. A fabric has no compressive force. It only has, or geogrid has only, or a fabric only has tensile force. And therefore, the designs that one makes or produces with these materials have to take that in consideration. When one builds a vertical face with a fabric or a geogrid, the face is not in tension. Anyway, this illustrates the construction technique in which the geogrid was laid down. This temporary form, which was 4 feet high, was used and braced, as illustrated on the slide, was plywood and stiffeners. And then, of course, the material that could be compacted with equipment was done with that kind of equipment, and then right close up to the front face, it had to be compacted with small equipment or hand methods. Let's go through the actual construction sequence of this. Here we see the embankment, which is actually getting close to the top, but this is where I have the sequence for the raising of the forms. Here are the forms that are laying flat, and then they're going to be raised. Pipes were driven through the geogrid, the lower layer. No problems in terms of making a few holes in this material or breaking a few strands, since it's not the ultimate design strength that is used for these materials. And so damaging, if you will, a few strands is not critical. Anyway, pipes were driven to give lateral support to this 4 foot high form. And in the early stages of the project, this is what the embankment looked like. It was a stair-step embankment. This was built, or started to be built, in the fall of the year, in a relatively dry period of the year in the Bay Area. As we look at the front face, and the front face is exposed to the sun, the material behind the front face, of course, dries up. And in this particular case, there was a fair amount of granular material, good from a shear strength point of view, but you start seeing some problems of the material actually flowing through the fairly open space of the geogrid. And if you look up close, you can start seeing that they were having some of these problems. And of course, the material, the geogrid itself, putting itself in the format that it really wants to work at, which is in tension. Here's the embankment that's being raised, again, still typically in the fall, and all the stair steps are in place. And this shows the form, the geogrid that has been flipped over the front face so that it will later be flipped back over the completed lift and for its embedment length. Of course, in the winter is the period where the Bay Area gets most of its rain. And it turned out that the whole project was not completed before these rains came into the Bay Area. And so the backfill started getting to be very wet. And as it gets wet, of course, it gets heavier. And as the forms are removed, of course, the material behind this vertical front face is getting heavier, and the geogrid is then starting to be put under tension. You'll note that there's a kind of a double lift in here. There was actually, within the 4-foot vertical lift, there was a relatively narrow strip of geogrid that was placed at the 2-foot level and tied to the front face for additional stability in this area. So as the form is removed and the material behind it gets heavier, the front face starts to slump. Ultimately, the connection at the intermediate layer was overstressed and broken, and the front face basically slumped, and the project ended up with its originally designed 3/4 to 1 front face slope, and therefore the steps on this embankment completely disappeared. Now, the embankment is stable. It's only the individual steps that have failed on this project, and so it shouldn't be looked at as a failure. But the point that I'm showing these slides is to illustrate that the contractor went through quite a sequence because of construction difficulties, and the final design, because he couldn't build what was originally designed, and he had to end up doing the stair steps, but ultimately the final slope was what was originally designed, but it's kind of a long way around to get to what the designer originally wanted. Here just some details of this material in the process of failing, and ultimately each lift slumped to its maximum angle until all the geogrid was placed in tension. Here's an overview of the slope during the winter. Some of the steps were smaller and haven't failed, but most of them have. Again, the embankment is stable. It's just the individual lifts at the front face that are not. Now, as the winter rains bring in some seeds, the seeds germinate, then you start getting vegetation on the front face of the slope, and here we see the grasses growing through. And of course, these grasses are going to shade the geogrid and protect it from further exposure to sunlight. And here it is in the next phase, where the grasses are getting thicker, and a long shot taken from across the valley, where the lower portion of the slide, you can see that the geogrids have completely disappeared behind vegetation, and the upper tiers, which were built more recently, are starting to get vegetated. This slide shows a later phase where vegetation is now taking over and completely masking that there is actually a geogrid system on the front face of the slope. Actually, this slumping of the front face, loosening of the front face, obviously allows the roots of plants to get in there and reinforce the slope more quickly. And here is a slide taken within the last few months, which show that the 2 lower tiers were right at the 3rd point up from the bottom here. That bench is where some people is at that level, have completely disappeared behind the vegetation, and the embankment looks quite satisfactory. The point of going through this is to illustrate that as one uses these geogrid materials, one wants to increase the lift thickness, and one increases the lift thickness, one introduces construction problems. The main reason, of course, for going to higher lifts is the fact that these geogrids typically cost quite a bit more than the geotextiles. Geotextiles, the commonly available geotextiles, the non-woven materials, can be obtained for maybe even somewhat less than $1 a square yard to maybe $2, and some of the woven, of course, quite a bit more than that. These geogrids On the other hand, their low end is typically around $1, but some of these higher strength reinforcement geogrids may cost $4.5 to $6.5 to $7 a square yard. And because of that, the designers want to use less, and because they're also stronger, they can be used for less. But in that transition period from going from these very low lifts of the geotextiles that we saw in the previous presentation, where we're only talking about lifts of 8 to 12 inches, to lifts between reinforcement of 2, 3, and 4 feet, we introduce these potential construction problems that have to be handled. This is another case history, also in the Bay Area, where the designer showed on the plans how these individual lifts were actually going to be built. The front face is also on a 3/4 to 1, and these vertical steps offset 4 feet high and offset by 3 feet are shown on the plans. In this case, they decided to put a geotextile behind the front face to again prevent this raveling problem that had been seen in the previous case history. Here we see the big compaction equipment away from the front face and the lighter type of compaction equipment closer to the front face. Just another detail of that. Again, note that there is a geotextile that has been placed in front of the geogrid so that the material will not flow through. The contractor used this kind of forming system and this kind of bracing system, relatively crude. Works fine for the first lift, but then you have to consider what's going to happen when you get up into higher lifts. Here we see the geogrid, which has been wrapped back over, and the next lift that's in the background that is going to be placed. Now, when you get up to the higher lifts, or the subsequent lifts, this system of bracing the form out, then you end up with either being in midair, which obviously will not give you any lateral resistance, or in this case, putting the force on the top of the lower tier. That, of course, adds a lot of force to the top of the lower tier, and if it's not properly supported, as you can see in here, you start losing lateral support, and problems started showing up in terms of keeping the proper alignment. And of course, when you remove the forms, the same things happen to this system. This is by the way, this is a different type of geogrid. This is what at the time of this project was being built was called Signode. I believe that they are being bought up by somebody else and maybe called something different at this time. Again, the geogrid wants to revert back to its to a position where it's being used to its fullest extent, which is in tension, and that's why you end up with the front face slumping out. Here is another case history. This is actually an earlier one than what I've just shown you, but the point of putting it in this sequence is it illustrates how an agency who tried to get the geogrid on an even steeper front face slope, instead of being about 3/4 to 1, this is about is going to be designed on about a 6 to 1. I mean 1/6 to 1, 1/6 horizontal to 1 vertical. So here is a small landslide. It's in a park area, and they're very environmentally conscious as to what the final product is going to look like. This is actually up in the Oregon coast, and here we see the slag material has been excavated, and then at the bottom they're starting to lay the first layers of geogrid to reinforce the buttress area. Now, as I mentioned earlier, this is a project that was built prior to the ones that I just showed you. At this stage of time, the only type of projects that had been built that were similar to this were engineering fabric or geotextile type walls, where a temporary form is used with the lateral support done by a temporary form and bracing system, which is an L-type system. And at this project, this is what was suggested be used to support these lifts between for the geogrid. Again, the lifts are going to be considerably higher than what was typically used for a geotextile wall, or thicker. And here we see that temporary form. It was just a welded piece of rebar with a vertical angle iron. And this is what was going to hold the front face in place. And here we see the first phases of construction where this type of bracing system was being attempted. Again, you can see the geogrid flipped over the front face, which ultimately is going to be wrapped around and is going to be the tie-down at the top here of this lift. Backfilling is starting, but very quickly the contractor realized that this did not provide enough support. What I want to show here is that, again, I mentioned earlier that the project was in an environmentally sensitive area in the sense of it's close to a park, and they wanted to get vegetation to grow on the front face of this geogrid wall. And what we see here is the placement of some grass placed against the front face, or behind the front face, sod that has been grown elsewhere and placed in the back here, so that the front face will have vegetation growing on it. You'll also notice that the backfill is a nice, clean, granular backfill, crushed basalt. Does not, however, provide a whole lot of nutrients for the front face of that material that is being placed here. Here we see the next phase of construction as the wall gets higher, but we also, if you start looking on the edge of the wall behind the face that is being formed, that the contractor actually had to go to a much stiffer and stronger bracing system than was originally planned. You could just not get the thick lifts that were originally designed within the tolerance that the designers wanted, and very extensive bracing system consisting of 2x4s laid horizontally in the fill, extending out to the front face and bracing the front face. Now, obviously, this required a whole lot more effort than was originally thought would need to be done for this project. That is very expensive to have to do this to get a very steep face. So what I've been trying to illustrate here is if you can get away with just the natural angle of repose where you can get some vegetation on it, then go that way. When you start steepening up the front face, going to 1-to-1, 3/4-to-1, or trying to go to a 1/6-to-1 front face slope, you start introducing some construction problems that one has to consider in terms of the overall cost of this particular solution for the use of these geogrids. Here's the end, towards the end of the project, and someone forgot to tell the contractor that they were supposed to water the front face of this embankment. As you can see, the upper layers are drying off. Even in this coastal area, they don't get a whole lot of rain, and during the summer months, and some of the grass dried up. And so that might be a consideration that you want to look at. Right now, and this is just about a year after completion, and several years ago, vegetation was coming back on the front face, and the wall is blending in terms of being vegetated. I do want to leave the audience with the fact that you can use these geogrids. They're good materials. They're excellent in terms of they have excellent engineering properties. You can build over steep and slope with them, but you need to take some extra construction steps to make sure that you can build them. What we see here on the slide is excavating the slope in steps and laying out the geogrid, and then wrapping it around the front face. And here there's a board that is being held by the bucket. That board has some nails on it, and the bucket operator is tensioning the geogrid in place, and the construction worker that we see in the back here is nailing this geogrid down so it's placed nice and tight before backfilling the next sequence. And this is done at every step of the construction, which leaves the front face of the slope with a nice, smooth, and well-contained front face. This is what it looked like after construction, and this is what that slope looks like now. This was done on private property, also in the San Francisco Bay Area. So they can be built. They work well. It just needs a little bit of extra construction effort to make sure that you get what the designer wanted and you get good compaction to the front face. Actually, each one of these steps was built over steepened and then trimmed back so that the slope would look nice and even and get good compaction. And just another detail of showing some handling of some drainage at mid-slope. Again, this slope, close to 1-to-1, doesn't quite look like that on this slide, but very difficult to walk on. And of course, with the grass on it and the slippery geogrid underneath, these slopes are difficult to walk on. Another application of a geogrid, a lighter weight geogrid we've seen before, but just a low type retaining structure. Again, it's this very steep slope off to the left, and would have been a lot of embankment material to be able to put a regular embankment here, and the designer chose to use this material, the geogrid, to build a small wall. It has a slight batter to it. You also note that in this case, the designer chose to put some pea gravel behind the front face. That gives you relatively ease of construction and compaction, and was able to build these relatively low walls, 5 to 8 feet in height, with a fairly steep angle, by again going to something that is easy to work with in the field, which is this pea gravel. Again, when you want to go to a steeper angle for ease of construction, apply and spend a little bit more money in a more expensive material that can be easily placed at the density that you want it, and so that you can get the alignment that you want. This is just another shot of this, and I have a close-up showing the pea gravel behind the geogrid. Obviously, you're not going to get a lot of vegetation growing, at least not very quickly, on a wall like this. Another solution to containing the front face is using railroad ties. And what we see here is a geogrid. This happens to be one of the other types. This is from Mirify. The designer here is using recycled railroad ties, and I'll show some more of this particular project later on in the recycled materials section. But basically here the geogrid is placed and nailed down to the top of the railroad tie, and the railroad tie and its weight is used to form the front face and get good compaction behind it. So that is another way of handling the front face problems that we have with working with geogrids, is to put some kind of relatively lightweight facing. So now we've got a geogrid reinforced backfill structure with railroad ties on the front face. Because the geogrids are fairly expensive, you would not put a lift of geogrid at the top of each railroad tie. These are typically 7 inches high by 9 inches wide, and you wouldn't want to be placing a geo grid at every 7-inch lift. So you'd actually go several lifts before going on and putting another layer of geogrid. This is that same structure getting close to completion. Of course, with a railroad tie front face, it's quite easy to build essentially vertical walls, of very slight batters. Here's, I think it's about ½ inch offset with each railroad tie. Several of the manufacturers of the geogrid systems, in this case it's Tensar, have developed concrete paneling for these systems. And so this is a concrete faced full-height panel that is being, with the backfill being reinforced with a geogrid. Of course, one of the problems going with a full-height panel and using a geogrid is that you want to make sure that the panels stay in alignment as you backfill the system. And to reduce the amount of lateral movement that occurs, then what needs to be done is that the geogrids have to be tensioned before they are backfilled. And this is what we see in these two slides, the previous one and this one here, where tension is being applied to the geogrid with these braces, and then backfill is dropped in between, and then the braces, of course, removed and going on to the next lift. And of course, you end up with a concrete faced retaining wall, and it looks like just any kind of other concrete faced retaining wall. So, in effect, in the beginning of the first presentation, I showed you some of the conventional lodge type structures, which talked about using metal strips and prefabricated concrete facings. Some of the geogrid companies have also come up with similar systems to use geogrids as a reinforcing with the concrete facing. And that concludes the presentation on using geogrids for ground reinforcement or